Present series of lecture we shall describe the numerical methods for solving ordinary differential equation. By ordinary differential equation we mean a differential equation in which the unknown function y depends on a single independent variable x. In contrast to this, in partial differential equation, the unknown function depends on more than one variables. And furthermore, we restrict ourselves to the linear differential equation. That is, a differential equation is linear in which there is no product term of the unknown function y or its derivatives, or no power, the powers of y or its derivative is not different from unity. This is the linear definition of linear differential equation. In this sense, the differential equation that we have discussed in our earlier theoretical part, that is Legendre, Bessel, Laguerre, Hermite, these all are ordinary differential equation. And later on we have started our discussion on Laplace's equation, which is a partial differential equation. To describe the method of in earlier classes or in theoretical part, we have discussed the analytical solution method for solving the differential equation. Here we shall discuss a method in which the differential equation under consideration is solved numerically. Rather, that is, in this case, in numerical solution, we get a value of y for a given value of x. We get a numerical value. We do not get the functional form. As for example, in analytical method, we may solve y and get y as a function of x, say x e to the power x. This is an analytical solution, but in numerical solution we will find the values of y, say it is 1.0, y of 0.1, then we get some other numerical values of y. This is the this is the technique of getting numerical solution. So we get the values for y at a given value of x. Obviously, the convergence of the result, numerical result, is a question. We shall start our discussion with the solution of first order differential equation, and then we shall consider two first order solution, numerical solution of two first order differential equation, and finally we shall elaborate our method for the solution of second order differential equation. So let us start with numerical solution of first order differential equation. First order differential equation. A general first order differential equation is dy dx is a function of xy. First order differential equation, say for example f of xy could be x into y, or it be 2x plus y, etc. And we are provided with us boundary condition with or in. So if we integrate this out, we will require one integration constant to be evaluated, and which is given by with y at x is equal to 0 is equal to y0, and it is known. As for example, say we say that at y is equal at x is equal to 1, y is 2. So this is the initial condition or the boundary condition. This is given. Our problem is to solve this equation. We rewrite this equation as dy is equal to f of xy dx and integrate it between the two consecutive values of y. Say we say y is this and y and x x1 is equal to x0 plus h. Our primary objective is to find out the value at this value. Aim is to y1 is that is y at x0 plus h. What is this? This is our aim to find. So keeping this in mind, we integrate it between limits x is equal to x0 to x is equal to x1. So we x is equal to x0 to x is equal to x1 dy. On the right hand side we have f of xy dx from x0 to x1, or we get this is x is equal to x1, that is x0 plus h. So we write y of x0 plus h minus y at x0 is equal to integration x0 to x0 plus h f of xy dx. The difficulty is that our aim is to find out y, and the y is involved in the right hand side through the function. As for example, this is y of x0 plus h minus y at x0 is equal to 2x plus y dx from x0 to x0 plus h. If we want to find out, perform this integration, then we need to know the dependence of y on x, which is our problem, which is basically the problem of solving a differential equation. So as we could not solve this differential equation, this functional form is not the functional form of y, or rather the dependence of y on x is not known. Such an equation is called integral equation. Coupled integral equation. The function y that has to be found out is involved within an integration which expresses y. So this is an integral equation, and in general it cannot be solved exactly. Once again, let me remind, if we know y as a function of x, then the basic problem is already solved. So we need not to go through this step. So y is not known, so we have to go for approximate methods. That is, some approximation has to be done so that we can find out a value of y, and then we shall go on improving the approximation. The first approximation, the simplest approximation, would be to replace f of xy by f of x0 y0. This is known because our condition is that we know the value of y0 at x is equal to x0. So we know x0, y0, and if we are provided with the functional form of f, then we know it. So this is the method, that is, we call y at x0 plus h. We take this on the other side, y at x0 plus x0 plus x0 plus h f of x0 y0 dx. This is the crude approximation, or the simplest approximation that we could do. Then we know the value of this. This is known as Euler method or Runge-Kuuta method of order 1. This is known as Euler's method or Runge-Kuuta method 1. Of order 1, Runge-Kuuta method 1, this is RK1. Let me go for the physical significance involved in this approximation. This is X, this is Y. Let the graph be of this form. This is the Y curve. We have a value of X at X0. This is X0 and this is let us call this is X0, and we have X0 plus H is over there. So we know this value Y0. This is the value of Y at X is equal to X0, and we are to find out this value. This is the exact value, Y1 exact. E means Y1 exact that we are looking for. dy dx is given by f of x. If we evaluate f of x at x0, y0, this gives you the initial slope. This is the slope. This curve has slope f of x0, y0. Slope is, this straight line is f of x0, y0. So we draw a tangent to the y is equal to y curve, and the slope of the tangent as evaluated at x0, y0 is this, which is nothing but this. And this is a constant part, and if we integrate it from x0 to x0 plus h, we get this much. So when we multiply this slope with this width, this is the width, so we get this is the change, or this is the change in y, that is delta y, which we call is, this is the change in y over y0. This is the change in y over y0. That is this part, that is, we have approximated the value of y to be like here, which I indicate by the red color. That is, in Euler method, we have approximated the value of y1 as indicated by the red color instead of the exact one denoted by black color, the y1e. So this is the approximated value, and let me call it y1 approximate. So here we get this value. This is the crude approximation. One may argue that instead of evaluating the slope at the beginning of the interval, we could evaluate the slope at the middle of the interval. That is, we could find out the slope at f of x0, y0 plus f of x1, y1 by 2. This is the average slope. And you see that what would be the value of y1? We cannot replace y1 by the exact value. In that case, we use this value of y1 over there. So for y1, we use y1 approximate, and we can get a better approximation, because in that case, the value of y is estimated from the slope at the middle of the interval rather than from the beginning of the interval. This method leads to the modified Euler method. And in such way we can go on improving the evaluation of this part. This is the increment part. There are complicated techniques for evaluating this complicated part. So what is our main aim? Our main aim is to find out this part y value of y at x0 plus h by knowing the value of y at x0. This involves an integral equation. The integral equation we cannot solve exactly. In Euler method we use the simplest approximation and replace the f by its value at x0 y0. That is, we estimate the value of y starting from the slope of the curve at the beginning of the interval. There are other methods which calculates the slope with better and better geometry. We are not going to the details of this method, rather we shall just write down the outcome of these methods. To be specific, we shall mention only the Runge-Kuuta method. There are four Runge-Kuuta methods, starting from Runge-Kuuta of order 1, which is nothing but Euler, and to the most accurately or most popularly used one, the Runge-Kuuta 4. We shall just describe these 4 methods and then apply it to a specific case. Now the different Runge-Kuuta methods are listed here. In Runge-Kuuta 1 or Euler method, we approximate y at x is equal to 1 by the value of y is equal to y at its value of x0 plus k1, the correction or increment term. The increment term is this, which we have shown you. This method includes, if we consider Taylor expansion, then it includes the functional value y at x0 plus h is equal to y at x0 plus y prime at x0 times h. So it approximates this plus 1 by 2 y double prime 0 h square, like this. This method, Euler method, includes or considers first these 3 terms. So it considers up to h to the power 1 term and ignores h square and other higher order terms. In that sense, the error included in this method is of the order of h square. Similarly, the order involved in Runge-Kuuta 2 RK2 is h cube. In this method, it is the error involved is h to the power 4, and finally the error involved here is h to the power 5. So if we make the value of h small, very small, then we see that the error involved in the evaluation of the function gradually decreases as the order of Runge-Kuuta method increases. If we consider h to be 0.1, then this is error involved is 10 to the power minus 2, minus 3, minus 4, and 10 to the power minus 5 order of error is involved in it. So we see that by decreasing the value of h, we could get appreciable accuracy by using Runge-Kuuta method of higher and higher orders. We shall apply this method to a very simple equation to demonstrate what the method is, and I will send you the detailed calculation in the WhatsApp group. The aim is to solve dy dx is equal to f of xy is equal to 2x plus y 2x plus y. The boundary condition is y at 1 is equal to 2. That is to say, and our aim is to find out what is the value of y at 1.2. This is the m. So f of x is given, f is equal to 2x plus y. H, the value we know, so x0 is 1, y0 is 2, and x0 plus h is equal to 1.2, that is h is equal to 0.2. This is the all about. In RK1, y at 1, that is y at x0 plus h, that is y at 1.2 is equal to y at 1 plus h f of x0 y0. That is y at 1 is 2 plus h is 0.2 into f of x is, this is equal to y0 plus h f of 1 2. So this is 2 into 1 plus 2. So this is 4, and the final result on simplification becomes 2.8. This is the value of y1 at y1 as per RK1 method. Now we use RK2 method. For RK2, we need to calculate first K1 is equal to h f of x0 y0. So this is 0.2 times f of 1 2, that we have evaluated just 0.2 2 into 1 plus 2, this is 4, 4 into 2 is 8, so 0.8. This is, and then K2 is h, K2 is h f of x plus h into f of x0 h y0 plus K1. So this is x0 is 1 and h is 0.2, so this is 1 f at 1.2, y0 is 2 and K1 is 2 K1 is 0.8, so this is at the value at 2.8, that is 2 into 1.2 plus 2.8. On actual calculation, this comes out to be 1.08, sorry, 1.04. So y1 is, as per Runge-Kuuta method, y1 is this, is equal to y0 plus half K1 plus K2. So y0 is 2 plus half of K1 is 0.8 and K2 is 1.04. So on calculation becomes 2.92. In RK3, K1 is same, is equal to 0.8. K2 in RK3, K2 is this much. H f of x0 plus h by 2, x0 plus h by 2, h by 2, y0 k1, y0 k1 plus by 2. So this is x0 is 1 and h is 0.1. So this is h into f of 1.1 at, and this is K1 is 0.8, so it is 2.8, so it is at 2.8 by, sorry, 2 and this is 4, so 2.4. y0 is 2, y0 is 2, and k1 is 0.8. So y0 plus k1 by 2 is 2.4. That is to say, this is equal to 0.2 into 2 into 1.1 plus 2.4 on explicit calculation. It comes out to be 0.92. Now come to calculation of K3. K3 is f. K3 is this fx plus x0 plus h. K3 is this y0 minus k1, y0 minus k1 plus 2k2. This is 0.2, f of 1.2. This is x0 plus h is 2. This is 2 minus 0.8 plus k2 is 0.92 into 0.92. So this becomes, this is equal to 3.04. Which comes out to be K3, the value of final value is K3 is 1.088. So the value of y1 is equal to y0 plus 1 upon 6 k1 plus 4 k2 plus k3. This is y1 is 2 plus 1 upon 6, k1 is 0.8, k2 is 0.92, 4 into 0.92 plus k3 is 1.088, and this on simplification becomes 2.928. You see that the number of decimal place increases as we increase the order of Runge-Kuuta method. Now finally we come to RK4 method. In this case again K1 is 0.8, K1, the definition of K1 is same in all the 4 Runge-Kuuta methods. Then come to K2, K2 is this much. K2 is h, f of x0 by h by 2 plus y0 plus k1 by 2. So this is same as the K0 of RK3 method. So this is equal to 0.92. You see that the K2 of RK3 and RK4 are the same. So we need not to calculate K2 or K1 separately. K3 is different in RK3 and RK4. In RK4, this is the x0 h by 2 y0 k2 by 2. Now this is 0.2, this is x is equal to 1.1 and y0 is 2 and k2 is 0.92. So this on simplification becomes 2.932. This is 2.46. That is 0.2 multiplied by 2 into 1.1 plus 2.46 on multiple explicit calculation. This becomes 0.932. And finally, K4 is h, f of x0 plus h and y0 plus K3. This is the formula. So this is y0 is 2 and K3 is this. So the final result is K4. For K4 is the 1.0664 and y1 is equal to y0 plus 1 upon 6 K1 plus 2K2 plus 2K3 plus K4 as per our K4 method. So this is 2 for y0, 1 upon 6. K1 is 0.8 plus 2 into K2 is 0.92 plus 2 into K3, value of K3 is 0.932 plus K4 is 1.0664. On simplification, this comes out to 9.284. This is the RK4 method, the value of y at this stage. One remarkable thing that you should check, that this is here the order is of the order of a square. So the first place has changed. Now coming to here from there, you see this place remains same. The change occurs in the third place, and if you go, the change occurs in the fourth place. So if we could decrease the value of y considerably, then we could get very accurate result by using RK4 method. That's why the Runge-Kuuta method of fourth order is very popular. In your syllabus, you want to solve the ordinary differential equation numerically by using RK4 method only. I have described all these or mentioned all these methods to make it clear to you how the improvement is achieved gradually by increasing the order of RK4 method. So never worry, you need not to require all these methods, but you are to remember this method only. Now the question that arises, if we want to solve the value of y, say at x is equal to 2 from this point, then it may be found that by setting the second value of x, if we set the value of x1 to be 2, in that case h would be 1. Since the value of h is very high, the error involved will be very high. So what do? We may go from x is equal to 1 to x is equal to 2 in suitable steps. Say first we divide it in h is equal to 2. Then we see what is the result. Then we decrease h to 0.1 and see how the difference is. If we set as I have stated, our m is from going from x0 is equal to 1 to xn is equal to 2. Initially we set h is equal to 0.2, so we solve the value at 1, 1.2 1.4, 1.6, 1.8, and then land up to 2.0. Now we set say h is equal to 0.1, and we get the value at 1.0, then 1.1, and in this case we land up ultimately to 2.0. So our aim is to find out the value of y at x is equal to 0.2. So there are two values available to us, both using Runge-Kuuta 4, one using step size 0.2, other one using step size 0.1. We'll then look at the difference between these two. If the difference between these two is less than the desired accuracy, then it's okay. Otherwise, we are to decrease h further, and this type of iteration has to be continued until desired level of accuracy is obtained. By desired level of accuracy we mean the estimated value of y at the point of interest, that is here in this example the point of interest is x is equal to 2. So we estimate the value of y at x is equal to 2 with two different h values, and we compare between these two. If the accuracy if the difference is less than accuracy is fine, otherwise we will take the value of y with lesser value of h, and we will recalculate the value of y at x is equal to 2 with still lower values of h, say is equal to 0.05, and we shall compare between the two values of y at the end point to check whether the accuracy is achieved. If not achieved, then we are to go for still lower values of h. This is the method of iteration. And if we could write a code using any one of the programming language, then the task is very easy. We set x0 is equal to 1, the starting point where the boundary condition is known, and xn is the point where we are to calculate the function, and we divide the interval into n equal intervals, and we may feed the computer the value of n, then it will calculate h accordingly, and will calculate the values of y at intermediate steps. The steps involved is that if we call this is x0, this is x1, this is x0, then x1. Then going from x0 to x1, we use this prescription. And when we want to know what is the value at x is equal to x2, then this value, that is this we shall treat, this is the starting value of x and the corresponding value of y. Say, as for example, if we want to know what is the value of y at 1.4, so recall that this is the value of y at 1.2. So what should be our starting point? Here the x0 value will be replaced by the value of this, and y0 value will be replaced by the y1 value. Will be replaced by the x1 value, which is 1.2, and y0 value will be replaced by the y1 value, that is 2.9284. This will be the starting point, and all this calculation will be repeated with x0 is 1.2 and y0 is 2.9284 to get the value at y2, and to get y3 value we again replace the x0 by 1.4 and y0 with the new value of y of 10 at x is equal to 1.2. So in this way we can go from one step to another step to ultimately reach the desired level of accuracy. That's all for today's class. I will provide you a handout for for the methods involved, and in this handout the very same example is being worked out in detail. In the next class we shall describe how to solve two first order ordinary differential equation by Runge-Kuuta 4 method, RK4 method, and finally we shall describe how to use the method to solve a second order differential equation.